The research paper discusses a bidirectional quantum teleportation (BQT) protocol that enables the transmission of even and odd coherent states between two parties, Alice and Bob. The protocol utilizes the multipartite Glauber coherent state as a quantum resource, leveraging the entanglement existing in symmetric and antisymmetric multipartite coherent states. The efficiency of the teleportation process is measured by the fidelity susceptibility, which is closely related to the quantum Fisher information, QFI. The authors demonstrate how the QFI can be used to estimate the teleported and gained parameters, highlighting the importance of entanglement resources and the choice of trigger phases for achieving high BQT efficiency. The paper also discusses the implementation of the suggested scheme on current experimental tools, emphasizing the role of quantum statistical speeds in improving the precision of parameter estimation. The research focuses on multipartite coherent states in the BQT protocol, particularly on their entanglement properties. It begins by discussing the concept of coherent states, their definition, and their application in quantum optics. The paper then delves into the specifics of multipartite coherent states, including their superposition and the importance of the overlap between states. The authors emphasize the distinction between symmetric and antisymmetric states, highlighting their significance in quantum technology. The discussion continues with the bipartite splitting of multipartite coherent states, detailing the creation of mixed and pure coherent states. The paper also explores the reduced density matrices, such as ρ12, and their properties, including entanglement. The concept of even and odd coherent states is introduced, and their use in creating an orthonormal basis is discussed. The summary concludes by explaining the concurrence, a measure of quantum entanglement, and its application in understanding the entanglement properties of the states. The research paper discusses the use of multipartite coherent states for quantum communication, focusing on the bidirectional quantum teleportation (BQT) protocol. It explores the entanglement properties of these states, particularly the concurrence entanglement, as a function of the coherent state overlapping and the number of probes. The authors analyze the behavior of concurrence entanglement for both symmetric and antisymmetric states, highlighting its variation with the overlap parameter p and the number of probes n. They also describe the BQT protocol, which employs even and odd coherent states to enable bidirectional teleportation between Alice and Bob. The protocol involves the use of 10 qubits, with specific steps including the preparation of trigger qubits, the exchange of even and odd states, and the application of quantum gates for entanglement and teleportation. The paper emphasizes the importance of the coherent components and the need for precise control over the parameters to achieve high fidelity in quantum information technology. In the proposed bidirectional quantum teleportation (BQT) scheme, a 6-step protocol is outlined for teleporting coherent states between two parties, Alice and Bob. The process begins with initializing the system in a superposition state and applying Hadamard gates to entangle the qubits. Subsequently, controlled NOT (CNOT) gates are applied to entangle the state, psi. With the triggers qubits, followed by Hadamard gates on even and odd to prepare them in an entangled superposition state. Then, both parties perform two controlled NOT (CCNOT) gates on the entangled qubit, psi, and storage qubits, CJ. The final phase involves applying Hadamard and controlled Z gates, as well as a phase shift gate, to the entangled state of the entire system. The fidelity of quantum teleportation, which measures how closely the transported state matches the original state, is analyzed in detail. The fidelity is influenced by factors such as the degree of entanglement, the quality of the quantum channel, and the measurement and reconstruction process. To demonstrate the significance of choosing the pre-shared entanglement state as a quantum resource on the teleportation efficiency, the variation of the fidelity with respect to the angle of both sender and receiver teleported coherent states nu(e)(O) for various values of the overlap parameter p, the number of partitions n, and the parameter m is depicted in Fig. 4. The fidelity increases as the coherent state overlapping p increases, with the minimum number of partitions n equals 3 required for this behavior to occur. For symmetric states, m equals 0, the fidelity reaches its maximum value if the shared resource is a separable state, p minus sign right pointing arrow 1. For antisymmetric states, m equals 1, the fidelity increases and the curves tend to be maximum when p minus sign right pointing arrow 1, and the shared resource state is reduced to a bipartite state of Werner type which is maximally entangled. This maximum value occurs for a maximum number of partitions, e.g., with n equals 25. When the shared resource between Alice and Bob is in a maximally intricate state, in particular a GHZ state, i.e., m equals 0 and p equals 0, the maximum fidelity is achieved during teleportation from an odd coherent state to an even coherent state. See Fig. 4c. Additionally, Fig. 4d shows that the fidelity is maximized when the shared state between Alice and Bob is a GHZ maximally entangled state. It corresponds to the antisymmetric state m equals 1 and the overlap p equals 0 with a maximum number of partitions n equals 25. These results provide important insights into the optimal conditions for achieving high-fidelity quantum teleportation between even and odd coherent states. These findings are crucial in understanding the behavior of the fidelity of our quantum system and can be utilized to optimize the performance of the BQT protocol. When we specifically focus on the case where n equals 3, and the overlap parameter p is set to 1, we observe a perfect fidelity with a value of 1. This implies that the teleportation process is flawless, and the teleported state is an exact replica of the original state. However, as we vary the overlap parameter p for different values of parameters m and the number of partitions n, we notice that p equals 0.2 and p equals 0.5 exhibit similar trends and shapes with different values for fidelity. Furthermore, our analysis reveals that the fidelity of quantum teleportation tends to improve as the number of qubits n increases, particularly at n equals 25 where we observe the interference of other parameters. FB right pointing arrow a at p equals 1 exhibits a slight curve, indicating that the quantum system is approaching the limits of its performance in terms of fidelity. The paper discusses the estimation degree of a teleported state in a quantum teleportation protocol, focusing on quantum Fisher information, QFI, and Hilbert-Schmidt speed, HSS. QFI is a measure of quantum information transmission and the sensitivity of a given quantum state to changes in the relevant encoded parameter. The authors also explore the connections between HSS and QFI, as they are two quantum statistical speeds connected to the Hilbert-Schmidt and Burrs distances respectively. In the context of the Bell quantum teleportation (BQT) protocol, the authors derive the analytical expressions for QFI and HSS of teleported states. They compute the three corresponding block vector components for both even and odd coherent states, which are essential in determining the QFI and HSS. The QFI is found to be a function of the parameters theta e and theta o, while the HSS is expressed as a function of QFI. The paper highlights the importance of these statistical speeds in assessing the credibility of the BQT protocol. It emphasizes that the higher the QFI and HSS, the more precise the estimation of the teleported state's parameter can be achieved. This research contributes to the understanding of quantum information transmission and the sensitivity of quantum states in the BQT protocol, providing insights into how to improve the efficiency and precision of quantum teleportation. The paper discusses the quantum Fisher information, QFI, and Holowososaki-Shor, HSS, for a bipartite quantum teleportation protocol using multipartite Glauber coherent states as the quantum channel. The QFI is calculated in both directions, from Alice to Bob and from Bob to Alice, under various parameters such as the number of probes, n, the overlapping parameter, p, and the trigger qubits phases, the and tho. The results indicate that the QFI strongly depends on these parameters, with maximum fidelity corresponding to minimum variance of the estimated parameter nu-e. Perfect fidelity corresponds to 0 QFI, where the variance of the Alice's trigger phase diverges. In the direction from Alice to Bob, the QFI increases with decreasing overlapping parameter p, while in the direction from Bob to Alice, it decreases. This suggests that when the information in Alice's trigger hand increases, the information in Bob's trigger hand decreases. A comparison between the QFI and HSS under the same conditions reveals that they exhibit oscillatory features and have minimum and maximum values that coincide perfectly. This implies that HSS can be used to identify the precise moments when the estimated trigger qubit phases reach their best estimates, making it a valuable tool for enhancing the efficiency of the bipartite quantum teleportation protocol in both directions. The utilization of multipartite Glauber coherent states as the quantum channel for bipartite quantum teleportation offers several advantages over other types of entangled states, including resistance to specific types of noise and decoherence, feasibility, and technical feasibility in experimental setups. These states are adaptable across a diverse range of quantum communication tasks and can be valuable components within quantum networks. In comparison to multihop states, multipartite Glauber coherent states demonstrate their advantages as a quantum channel, particularly considering the impact of noise and signal diminution during quantum transmission. The selection of the right quantum channel emerges as a critical determinant in the field of quantum communication, with the unique advantages of multipartite Glauber coherent states being reliability, simple encoding, integration with classical communication, decoherence reduction, and suitability for distributed quantum computing. The proposed BQT protocol offers a novel approach to quantum communication, leveraging efficient resource utilization and unique properties of coherent states. By examining previous studies, particularly Ref. 85, we can appreciate the advantages of our BQT protocol. It achieves a maximum fidelity of 1 under specific conditions, demonstrating efficiency and resilience. Our approach differs by treating the whole system state as a quantum resource, allowing for maximum fidelity through parameter optimization. The protocol's experimental implementation on Qiskit demonstrates its practicality and potential for secure, long-distance quantum communication. The circuit's description and simulation results show an equal probability of measuring the quantum system in the corresponding classical states, indicating the protocol's efficiency and effectiveness. This equal probability is a result of the balanced nature of the circuit, including the application of Hadamard gates for superposition and controlled Z gates for entanglement. The BQT protocol's ability to achieve high fidelity and its practical implementation make it a significant contribution to the field of quantum communication. The research discusses a bidirectional quantum teleportation scheme for simultaneously teleporting even and odd coherent states in 2 directions through the multipartite Glauber coherent state. It examines the amount of entanglement in the shared resource state, finding that concurrence entanglement increases with higher values of overlap parameters. The efficiency of the protocol is evaluated via fidelity, with a minimal number of probes required for maximum fidelity. The study also compares the QFI with HSS, showing a similar role in enhancing the efficiency of the BQT protocol in both directions. The relationship between QFI and fidelity is established, with higher fidelity leading to a more accurate estimation of Alice's trigger phase parameter. The authors highlight the importance of probabilities in the context of coherent state teleportation and demonstrate the efficacy of the protocol using IBM QASM, IBM Air, and Bellum simulators. The research concludes by emphasizing the need to control environmental effects and to explore the implementation of the BQT protocol in noisy channels. This research paper explores the concept of bidirectional quantum teleportation using a hybrid approach that combines the utilization of W-type entangled coherent states and a 5-qubit cluster state as quantum channels. The authors demonstrate how this method can enhance the efficiency of quantum information processing, particularly in the context of multi-hop communication networks. By employing quantum entanglement and decoherence, the paper highlights the potential for improving the fidelity and efficiency of quantum teleportation protocols. The paper begins by discussing the importance of quantum teleportation, a fundamental concept in quantum information science, which allows for the transfer of quantum states from one location to another without physical transport of the particle itself. It then delves into the specific case of bidirectional quantum teleportation, where 2 quantum states are teleported in opposite directions simultaneously, utilizing entangled quantum channels. The authors emphasize the role of quantum entanglement, a key resource for achieving quantum teleportation. They introduce the concept of W-type entangled coherent states, which are generated through a combination of quantum entanglement and classical correlations. These states are shown to be highly efficient in enhancing the precision of quantum teleportation, especially when used in conjunction with 5-qubit cluster states. The paper also discusses the impact of decoherence on quantum teleportation, an inevitable process that causes quantum information to be lost over time. The authors present various strategies for mitigating decoherence, including the use of error correction codes and dynamical decoupling techniques. They further analyze the performance of their proposed protocol under different decoherence models, demonstrating its robustness against environmental noise. Moreover, the paper addresses the issue of quantum estimation theory, focusing on the quantum Fisher information matrix as a measure of the sensitivity of quantum states to parameter changes. The authors derive analytical expressions for the quantum Fisher information matrix for multi-qubit systems, providing insights into the optimal strategies for quantum parameter estimation. In addition, the paper touches upon the subject of quantum computing, emphasizing its potential to revolutionize various fields such as cryptography, simulation, and metrology. It highlights the importance of developing efficient algorithms and protocols that can fully exploit the power of quantum mechanics in solving complex computational problems. Finally, the paper concludes by discussing the limitations and future directions of the proposed bidirectional quantum teleportation protocol. The authors identify potential avenues for improvement, including optimizing the entanglement generation process and enhancing the robustness of the protocol against various types of quantum noise. They also suggest exploring the application of their method in real-world quantum communication systems, paving the way for more efficient and reliable quantum information transfer.